Let's calculate the initial pH prior to the addition of any titrant. So we need to remember here that although our concentration of acetic acid is 0.100 molar, it is a weak acid, so it will not fully ionize. We need to create an ice table for this question to determine the hydronium ion concentration. I'm going to let you follow along as this is something we have done before. In this problem, we're going to calculate the pH just before the halfway to equivalence point. So we've added 12.00 mils of 0.1 molar sodium hydroxide, and we've added 25 mils of 0.10 molar acetic acid. So we're going to start this problem by calculating the initial concentrations of my acid and base, taking into account the dilution effect. So I've got 0.100 molar acetic acid, and I'm multiplying that by 25 mils divided by the 37 mils that is now the total volume to get 0.06757 molar. I'm going to go ahead and do the same thing with the sodium hydroxide. Next, I'm going to set up an ice table to show how these are going to cancel out, my acid and base are going to cancel out. So I've got sodium or acetic acid plus sodium hydroxide yielding sodium acetate and water. I'm going to ignore water in my ice table, as always. And as we can see here, my acetic acid is in excess over my sodium hydroxide. That makes sense, I'm not at the equivalence point yet. So the sodium hydroxide is going to be completely neutralized. I'll be left over with an excess of 0.03514 molar acetic acid, no sodium hydroxide, and 0.03243 molar sodium acetate. And so what we want to recognize here is that I now have acetic acid and its conjugate base. So this should look a lot like a buffer situation. And so since I have a buffer, I can use the Henderson-Hasselbalch equation to calculate the pH, where the pH is the pKa plus the log of the conjugate base concentration divided by the conjugate acid concentration. So that's negative log of 1.8 times 10 to the negative 5 plus the log of that ratio. And we end up getting 4.71. So slightly below our pKa. At the halfway to equivalence point, we should recognize that the acetic acid concentration is now going to be equal to our acetate ion concentration. So that ratio is now 1 to 1, which means that when I use the Henderson-Hasselbalch equation, this is going to simplify to the pH equals the pKa plus the log of 1. And the log of 1 is 0, therefore my pH is just going to equal the pKa whenever I'm at the halfway to the equivalence point. So in this case, since I'm using acetic acid, I'm going to take the negative log of 1.8 times 10 to the negative 5, since that's its Ka, and we get 4.74. So at the halfway to equivalence point, the pH is equal to the pKa. In this problem, we're going to calculate the pH just beyond halfway to the equivalence point. So we're going to set up this problem exactly the same as the previous ones. So I'm going to turn off my video and let you guys follow along. So it's important to note some of the trends that are happening in this buffer region. So if we're before halfway to the equivalence point, my pH should be less than my pKa. If I'm at halfway to the equivalence point, then my pH is equal to the pKa. And if I'm beyond halfway to the equivalence point, then my pH should be greater than the pKa. And we can see that in these three problems as the ratios of the conjugate base and conjugate acid are changing.